This is the third of the 3-video series on processes and process management. The video begins with a brief recap on context switch and process switch in light of the privileged mode of the kernel. The video further discusses some of the advanced concepts of how to represent a process in the operating system and ends with a discussion on some aspects of process scheduling queues and process schedulers. This is the content. We will talk about the life cycle of a process, which are the states through which a process undergoes. This essentially is the state diagram. We will also talk about process control block to understand representation of processes in the operating system. The video then talks about process schedulers. The video will end with a brief note on threads. So as we know that a process is an instance of a running program. And before that, the program is residing in the disk drive, and we can see it through the little nice icon before it is launched and loaded into the main memory, right? So after it is loaded into the main memory, now it has changed its status from passive to active state. At any time, there are multiple processes running concurrently, and the operating system allocates each of the process some memory resources, also called the address space, that includes different segments for the code, data, and state used for function calls. And basically, an address space is a chunk of memory that is available to the process somewhere in the memory. This is the address space that communicates with the CPU or processors, to execute the processes that are selected by the operating system, or in other words, the process that is in the running state. And shortly, we are coming to process state diagram to see the life cycle of a process. The code segment contains all the compiled instruction of a given process, and the static data that is never going to change and is compiled into your program. That is going to reside in the data section. Then we have the heap used for dynamic memory allocation, the part of data that is allocated in runtime. And the stack is the region of memory used for procedure calls in your programs. So these are the accessible range of addresses of a particular process, plus all the state associated with them, such as instruction pointers, the stack and base pointers, and all other general purpose registers. And the operating system periodically context switch between active processes to allow them share the CPU, in which case the CPU is now communicating with the address space of that process. That should be easy, right? The context switch is also used as a way of communication with the kernel using system calls in case the user process wants services like accessing the disk drive or data comes from the network. As we have already talked about the minimal set of state information known as the execution context, which must be stored to allow a process to be stopped and restarted. And we also know that this information is stored in the main memory, right? So these are the processes that we are interested to execute in the main memory, shared by the processes and accessed by a single processor. Before we go any further, let us differentiate between a process switch and a context switch. Though process switch and context switch are interchangeably used, but actually there is a difference. Switching between processes on a system is often called context switch, although a process switch is a more precise term. The operating system can perform a context switch from a process into a section of the kernel and then back to the same process without actually performing a switch. So in context switch, the context switch requires at least one mode switch to perform, since the CPU must switch to the supervisor mode to enter the kernel mode. Relatively speaking, the context switch are computationally expensive operations, and frequent context switches may reduce performance. Whenever the operating system wants to switch from one process to another, it must first make a context switch into the kernel. The kernel then saves the state of the previously running process and restores the state of the process to which it is switching. A second context switch is then required out of the kernel to start the newly restored process. So these are the two switches. These are the two context switches required for a process switch. I hope you understand the difference between a context and a process switch, right? So we need two context switches for that. So in a uniprocessor system, the operating system has to switch the execution context between multiple processes using the context switching mechanism to give an illusion that we have a bunch of processors to service all the processes in parallel. And because we have been using the terms user mode and supervisor or the kernel mode, so let us just have a few words on the kernel mode. This is a very high level view of the Unix system structure. These are the three pieces of a Unix operating system organization: the user mode, the kernel mode, and the hardware. In user mode, we have restricted commands that don't have full privileges. The shells and commands, compilers and interpreters and system libraries resides in the user part of the system that helps user applications to run in our computers, okay? On the other hand, the kernel part of our system is the most powerful aspect of the system. And this is where all the secure things happen. This is where the process scheduling happens. This is where the file system is built in. The device drivers are implemented in this part of the system, etc. Okay, and the hardware is, of course, the actual hardware that our applications need to interact with, usually through device drivers, right? This actually points out to the two modes that leads to an obvious division of code into those things running as user mode and those things running as the kernel mode. So kernel mode has special privileges and is responsible for the very important concept of sharing computer resources among multiple processes through the context switching mechanism. So in order to go from the user mode to the kernel mode, you will have to do something very specific. You will have to do something very specific using the system calls, and the kernel returns back to the user after handling the user request. Let's look at this from an even higher level of abstraction to understand the communication between the user and kernel modes. So this is probably the highest abstraction to understand the user interaction with the kernel. So we can think of the kernel as being a small piece of specialized code that is very carefully debugged and tested, and hence reliable. The user program, on the other hand, is not reliable and needs a controlling body to allow it access to different components of the system or resources, okay? The bricks here are the hardware resources. Some have limited access and some have full access. The hardware can only be accessed through the kernel. So we are going to have to make sure that when we enter the red zone, we are executing a code that has been verified and has undergone a lot of debugging, okay? So how do we run a program? Well, we will have to do an exec call from the kernel mode out to the user mode. And the user mode would eventually exit to the kernel mode. So everything is centered around the kernel, right? So the user can only interact with the kernel using system calls, which are a controlled gate into the kernel. For example, the user might want to open a file using the system call open to read or write into the file. And then a return from the system call returns back to the user and you can read-write a file. So we made a file system basically read a file through system calls, and it returns a handle to that file. And interrupt is also a good example where some hardware says I need some service, and the user without knowing causes an interrupt to go to the kernel mode, and the kernel mode handles the interrupt, deals with the hardware, and the hardware finishes, and then eventually we return from interrupt and back to the user mode where the process can start from where it left. And then finally, we also know about exceptions from our first video in this series, such as a divide by zero gets you into the kernel where the kernel aborts your program. Okay, so the system calls, the interrupts, traps, and exceptions are the three types of mode transfer, things that switches between two modes that we know, right? These are also called unprogrammed control transfer. Where does it go? The system target address of these unprogrammed control transfer is found in the interrupt vector table from one of our earlier videos. The exception handler code can only be accessed in the kernel mode. So let us look at what a process does when it is in the kernel. So the process has a life cycle that is explained using a state diagram. As the process executes, it transitions from state to state. When you create a process, remember in Unix, a process is created using the fork system call. So after the operating system allocates it an address space and gets all its register state initialized in the process control block, we will shortly come to what is a process control block. The CPU processor scheduler determines when and where the process will be run. So now it is a valid process and is eligible to get admitted into the system, which means that it is admitted to the ready state. That means it is ready to execute when the processor is available. The CPU scheduler determines when and where the process will run. Based on the scheduler decision, the dispatcher might start the process by loading it into the processor. And now the process is in the running state. Or in other words, the instructions of the process are being executed by the CPU. Okay? And while running, there would be an interrupt of some sort, in which case we go back to the ready queue, meaning that the process is not running anymore. However, at any instance, one process is always running on the processor. We wait for our turn and do this for a while. And then at some point, we may need to communicate with the I/O device. For example, the process wants to read from a disk, and that is slow, and we know that. Yeah. So we don't want to stall the process. We don't want to stall the processor while the disk is being accessed. Okay. So we put the process in a different queue that is not the same as the ready queue. Okay. The ready is actually for processes that are ready and waiting to run based on the scheduling policy of the operating system. The processes in the waiting queue says that I'm not ready to run and that I am actually waiting. So when the I/O is complete, the process is again when the I/O is complete, the process is again put to the ready state, and eventually gets time and eventually gets the processor time again. And then for a while, it transitions between the running queue and the ready queue. Basically, the context time that we talked about earlier is the typical cycle time between the ready and running queues until the process finishes, in which case it terminates with an exit call. But as we said in the previous video, that these processes still consume resources, including various tables maintained by the operating system. So it is in a zombie state, okay? And please note that the queue here is only a buffer that holds these processes. It is not necessarily FIFO, which is a scheduling algorithm to get things off the queue, okay? So this is an important distinction. And why would a process stay stuck in a terminated state? Well, because we are waiting for the parent to read its return code from exits that is put in the process control block. And we don't want to get rid of the process control block until that return code is put somewhere, okay? So now we know why our zombies formed, right? And that brings us to the process control block, which is some sort of mechanism that keeps a track of these processes and the state they are in. So what is a control block? So what is a process control block? In order to understand how processes are actually scheduled, we first need to look into what is this process control block, abbreviated as PCB. Well, it is a way how processes are represented in the operating system, meaning each process is represented in the operating system by a process control block. So whenever we create a process, it gets a PCB of its own, okay? A process control block is basically a data structure used and maintained by the operating system to store and manage all the information about a process. It is also known as a process descriptor, just like we had a file descriptor for representing files and directories, right? This information is used for various process management activities, such as those during the state transition that we saw earlier. The process state is continuously updated. So what information does a PCB actually contains? The process control block have things like the process state, process privileges, process number, process counter, registers, and memory limits, and list of open files, and so on. So let us look into this diagram and try to understand the entities in it one by one. We have the process state, which tells us about the specific state in which a process is at that particular moment. A short while ago, we talked about the life cycle of a process and the different transition states using a state diagram, such as ready state and running state, waiting state, terminated state, and so on. So the process state will tell us which of those states is the process in at that particular moment. Processes have various privileges. So this block represents process priorities, and this information is used to give processes access to non-CPU resources. The process control block is identified by an ID, the PID that we discussed in our earlier videos, which is a unique number given to a particular process. Using this ID, the operating system will identify a particular process. This is one of the things that is in the process control block, okay? This block has certain pointers that point to the parent process, as well as we have pointers pointing towards the children processes. Then we have a program counter that indicates the address of the next instruction that has to be executed for a particular process. And we know that a process is nothing but a program in execution. And a program is a collection of instructions that are executed line by line. So which instruction in the process to execute is actually tracked by the program counter. And this is one of the things, that needs to be saved during the context switch. One of the other information that needs to be saved during the context switch is the CPU registers. Recall that the CPU registers are temporary storage used for intermediate computations. And the most important of these registers are the ones used for addressing different segments of the address space allocated to a process. The next one that we have is CPU scheduling information that has information about the priorities of the processes, and based on these priorities, processes are taken off different queues or states and loaded in the processor. So basically this block has a pointer to the scheduling queue and also other scheduling parameters. That is a pure topic of operating system. Next, we have the memory management information. So the memory management information, as the name implies, that it represents the memory that is being used by a particular process. So different aspects of the memory all those information regarding that will be stored in the memory management information, such as the page table information, memory limits, etc., are stored in memory management information block. We also have space for accounting information that keeps an account of all those resources that are being used by a particular process for its execution. For example, CPU time used. So this is also another thing that is there in the process control block. The process control block also have the IO status information. That is a list of IO devices that are allocated to a process because a process might need to do an IO operation, and this is also a part of the process control block. So this is the data structure that is called the process control block and is required by the operating system to represent and manage our processes. So I hope with the understanding of process control block, we have further consolidated our previous knowledge about processes and how are they managed, right? Recall that this is the information highlighted in yellow that is used for saving the process CPU state when switching between two processes. Okay, so when the operating system switches between two processes, this is what actually happens. We already talked about this in the second video of the series, right? You can pause the video here and make sure that all this makes sense to you. A few words about process scheduling. Now we are interested to see those things through the glasses of a process control block. Yeah. So each queue is a linked list of process control blocks, and we have multiple linked lists for the different queues. So all the PCBs are at all time in the job queue, or what is also called the new queue, that contains newly created valid processes ready to be admitted into the system. This in fact means a linked list of process control blocks ready to be admitted into the system. The process control blocks corresponding to processes in the ready state are linked into the ready list. The processes waiting on IO devices have their PCBs linked into various different device queues. These processes migrate between the ready state, device state, and the CPU during scheduling and execution. These linked lists are used and maintained by the operating system for process management. Okay, let us briefly view a diagram to understand the concept in more graphical way. In this diagram, we can see the PCBs for 5 different processes. All PCBs are members of the job list or the new list, and its linked list are depicted by the green arrow. 3 jobs are in the ready list, and 2 jobs are in the device queue, waiting on IO. The linked list within each queue are represented by the black arrows. Notice that the 2 linked lists for the queues are also linked list for the job list or the new list. Careful management of these linked lists is a major requirement of any operating system kernel code. Now let's shift gears to discuss process schedulers. In the operating system terminology, we usually divide scheduling into 3 types: long-term or job scheduling, mid-term scheduling, and short-term scheduling. Job or long-term scheduler refers to scheduling new valid processes into the ready state or the ready queue. This kind of processes have long intervals, usually an order of seconds to minutes. Mid-term scheduling refers to swapping of inactive processes out of disk and restoring swapped processes from disk on demand. CPU scheduling or short-term scheduling refers to the selection of processes from the ready list to run on CPU cores. These are usually measured in milliseconds. The one piece that is missing yet is the dispatcher. What is a dispatcher? It receives the process control block from the short-term scheduler and restores the context to the process. The dispatcher also completes the context switch to the process by performing a mode switch to the user mode and jumping to the instruction address specified by the newly restored program counter. Just for the sake of completeness, I leave you with a one-liner note on threads. The processes are further divided into threads, which basically means the execution context is further decreased, improving efficiency of processes. These threads are lightweight as compared to a process and are maintained by the operating system and are maintained in thread control block and can be managed independently by the scheduler. A thread shares information like data segment, code segment, open files, etc. with other threads of the same process, while it maintains its own registers, stack, counter, etc. In the end, I encourage you all to look into the difference between a process and a thread and make yourself comfortable with this powerful idea. I hope this series of videos were helpful. Thank you.